So we are Women Who Code Python. And now sorry, I'm still having problems this morning. Maybe I should slurp some more coffee. It's morning where I am. I know it might be evening or afternoon for most of you, but I'm in an earlier time zone, and I clearly have not had enough coffee. All right. Our mission with Women Who Code, we are a global not-for-profit. We're dedicated to inspiring women to excel in technology careers. We have 4 general goals. We want to empower women with the skills needed for professional achievement, educate companies to better promote, retain, and hire talented women, build a global community where networking and mentorship is valued, and develop role models and support this generation of engineers. But it's not just engineers. We want to support all women who are connected to the programming and engineering field and to STEM and STEAM fields. We do have a code of conduct. We are an inclusive community. We're dedicated to providing an empowering experience for everyone who participates or supports our community. And that's regardless of your gender identity, your expression, your sexual orientation, your ability, your physical appearance, your body size, race, ethnicity, age, religion, socioeconomic status, caste, creed, political affiliation, or even your preferred programming language. We really love Python, but we understand that there is more than Python out in the world. Our events are intended to inspire women to excel in our technology careers, and anyone who is there for this purpose is welcome. We don't tolerate harassment. The full code of conduct, which applies to all of our events and online communities, can be found at womenwhocode.com/code of conduct. There is also an incident report form if you encounter anything you consider harassment at any of our events or in our online forums. We have more than just this one track. The Python track is one of 6. We also have front-end blockchain, mobile, cloud, and data science. And these tracks are our online global tracks focused around specific technical topics. We also have locale-based in-person meetups in different cities around the world. And we'd like to thank our sponsors. Without them, this would not be possible. And those are McKinsey & Company, the Python Software Foundation, Home Depot, Atlassian. These are all great companies, and yes. And welcome to ML Mondays. And this session, we're going to be covering some math for ML. And this is hosted by Yashika, Liliana, and myself, Bethany. And we're gonna start, and this is a little bit about the study group thing. Those of you who joined us last week heard about this. This is just a kind of a brief recap of that. We want this to be semi-regular, and ongoing. We expect it to be fun, and we want to increase our knowledge together. That means if you hear me saying something BS or I'm wandering away, you bring me back. And we bring each other back. Anything that you want to bring to the session to discuss, or any of your expertise that you want to share, we want to encourage you to do that, because the best way to learn is to learn together. And that leads to the next step. This is a collaborative group. So we kind of want to work on things together if we can manage to do that. This is not where you listen to a complete presentation from an expert, especially not me. I am not an expert. We're here to learn, and we're here to work through the material, and there is a mountain of material. And so it would just be great if we can do that together. And we're not going to be creating notes or slideshows really for this study group, but we are recording the session, and we will provide a repo for community notes and code. Oops. And this is just a little recap from last week, a general definition of ML. And with that, I think we, Liliana, if you haven't, we probably want to start the recording for people who I
already started it. No,
you already started it. Okay.
Yes.
Awesome. That's perfect. And at this stage, we've planned a little bit of time for those of you who joined us last week and who were working through that Python notebook that you heard me whining about at the beginning of the session. If there are any questions or issues, or anyone has any general questions about Python and that Python Whirlwind tour, before we kind of start digging into the fun part of the session, which is math.
Woo!
Woohoo, math, yay! Which is a fun and terrifying, I'm totally lying if I say I'm not terrified, terrifying subject, but yeah, so anyone who is joining us who has some questions about Python, or questions about the notebook, or questions about the homework, if you decided to tackle that, please type them, chime in, give a talk about it. And while we're doing that, I'm going to see if I can open up a prayer commit of that notebook.
Is anyone here that is their first time joining the study group? Now we got 2 people. Okay, so we might want to share that notebook to them so they can take a look at it later.
Yeah, when I fix the notebook, you'll be able to pull it straight off the repo. The problem we're currently having at the moment is that it isn't opening. And so I need to back up to a commit that I haven't screwed up.
Oh, okay. That's okay. In the meantime, is everyone, because we are running this study group, we also have a Slack channel, and we want you to be part of it because we have the Slack channel in there, and we can talk things there, and we can also share information there. So if you are not in the Slack, let us know and we can add you. And also if we don't get this notebook working, we can share it over there after the session whenever it's working.
Sure. All right, I don't think I can do it from the repo. So let me see if I can back up on my computer and do a backup of that. But also, even if I can't, well, let me just pull it up.
So Bethany, my Evelyn is asking if we are not using that repo. So is there something in that repo that wasn't updated the past few days?
Yes, I pushed a new update, but Maybelline, thank you. I think you've just given me the hash. I was looking for the hash from the last time I
yeah, that's the one.
the last time I did a push, because the last time I did a push, it actually was good. So I had just updated it today and hosed it. So let's see if that one actually works. This afternoon, I was pushing a last change to the math Jupyter notebook, but something on my machine, no, that hash Maybelline actually is telling me that that's the correct one. All right, let me do one more last digging. I need to just get into my Git on my machine and do a reset head here.
Yeah, Emily, we had a little issue with the notebook, so we are trying to solve the problem, and we will share the notebook soon so everyone can see it.
Yeah.
So Bethany, is the notebook the one for last week, the one you did changes for?
No, the notebook that I did changes for was the one for this week, but it created a merge conflict that appeared to be resolved. But in resolving that merge conflict, it screwed up the notebook.
Okay.
So I need to back up one commit. And
yeah, I was asking because I wanted to share the one from last week for the new people because they haven't seen it the first time.
yeah, and so it needs a specific commit hash. And I
Okay.
thought I had the right hash, but I don't have the right hash. So I'm trying to quickly find the right hash. And of course, it's incredibly painful when 25 people are listening. Yeah, so I apologize. But I think what happened here is I did something I added a link in that notebook and I tested it, but something went wrong. So
It happened to me when I was speaking in the data pie, and I did a change the last minute and everything got complicated.
Yeah, so there's a stash change here that appears to have really screwed up the notebook. All right, 2 seconds. I'm hoping.
Yes,
If not, then we'll skip to this week's. I'm sorry, go ahead.
Yeah, I just wanted to say to Maybelline that I know that you have the old one, but she did some changes in for the new one, so that's why we wanted to use the new one. I was just letting her know.
So Maybelline, that thing that you just pasted into the channel, you are able to view that right now. That hash commit is not creating problems for you, because when I tried that hash commit, it created problems for me. So that's
if
the
you're
deal.
not running it in GitHub, it opens. I mean, I'm just opening in GitHub. Which notebook are you trying to open? The one that is Python whirlwind or the one that is math?
The Python one. Yeah, the Python one is host. It won't open.
Are you going directly to GitHub or are you going?
No, I'm launching it in Binder and I'm launching it in Colab, and they won't. And I'm actually launching it on my machine and it won't load. It crashes. So
yeah, it doesn't work. The original one, the first one.
yeah, it's dead.
Yeah, the math.
It has some sort of it has a let me see what error it is tossing. It's stinky enough that it won't even like it's crashing Jupyter on my machine. Give me just a sec. Yeah, so I think we're going to have to give up here because we're 21 minutes into the session. And so I think what we're going to have to do is maybe defer our questions about Python. Notebook does not appear to be JSON in cells. So the problem is that whatever it's trying to load or resolve, it hits a cell. Don't know which one. If I knew which one, we could delete it. I don't know which one. And so, all right, let's try this. I have a suspicion about which cell it is though. So maybe I should go look at that cell, but this is the last thing I'm going to try because I don't want to waste everyone's time with me kind of just talking through how I'm trying to, yep, there it is. Well, of course it's not. Oh man. Okay. Yep, I think I found it. Let's see if that works. When Git resolved the conflict, it put a note in the file, and the note in the file was not helpful to Jupyter. Can you imagine that, people? Yay! Yeah, it inserted something. So let's see if that unhoses it. Yep, okay. All right, let me push this change. That was dumb. Okay. All right, ladies, this is where you have to be careful to not swear in your commit messages, even when you're tempted to, because they're public. Oh, I want to type a swear word in here quite badly. Next, okay. All right. I think, let me just double check this. All right, 19 seconds ago. Let's go to the link. All right, Binder, while we're young, come on. I know it's not your fault that I screwed up the notebook, but really. Okay, I've pushed that change. If any of you out there want to try accessing that notebook now in either Binder or Colab, it ought to work.
Yep, it works.
Good. At least that's something. Mine is still loading.
Have you shared the link to people, because maybe they don't know what it is, because not every, we have some.
Yeah, if you could share out I've got Binder taking up my whole screen at the moment. Can you, Liliana, share the link to
Yes, I did.
the
So
repo, not the Women Who Code one, but the one in my repo. The Women Who Code one points at the bad commit.
No, I'm just in the Women Who Code one, and it opens in Colab.
Oh, okay. So it pointed at the right commit. Okay. Yes. Well, I'm not going to argue then.
You go there. If you go there to that link I sent, you have some titles in there, quick links on their notebooks. We are talking about the first notebook. You can open it in Colab, or you can launch it in Binder.
Yep. It will now no longer complain because it doesn't have the turdlet that Git left in there.
All right, let's get to it.
Yep. Well, I mean, that's my whole thing though. Does anyone have any questions about this notebook? Because if no one does, then we can go ahead and have Yashika move on to the math notebook. I think we agreed last time that people were going to kind of look at this notebook and work through or look over the content and bring any questions that they had about it back. And for those of you joining us for the first time, this is just a basic whirlwind tour of Python. We didn't really want to bore anyone with like a whole bunch of details about Python. We kind of assumed people were spread out in their understanding, and that anyone who needed extra help with kind of getting up to speed would pop into the Slack channel or ask us, or you can ask your questions here as well. Oh, Binder seems to think I'm blind though. Holy cow. This notebook is like at 200% for some reason. All right.
Any questions, anyone? And if you haven't checked the notebook because you were not in the last time, we already shared it, so you can go ahead and check it out after, and you can still ask questions in the group later.
Yeah, and this is sort of there's a Python tutorial in the Python docs, and this generally covers the same material as that. It's a rundown of all of the things that you kind of want to know in core Python.
I think people want some math.
Okay, well, let's do some math. Yoshiko, do you want me to share, since I'm in here, do you want me to share the math notebook, or do you want to go ahead and do that, and we'll get people started?
Works either way. I can share my notebook as well, and you can share it too.
Okay, I'll go ahead and stop sharing, and you can go ahead and share the fun math notebook. And just to let people know, the strategy we've taken here is this, again, is going to be kind of a very fast overview with some resources that we hope you'll start to dig into. And then next session, we're going to dig in some more, because there's no way we can cover all of this in 40 minutes. It's a lot of math. So go ahead.
Give me a second. My kernel is not connecting.
Your kernel's not connecting. Do you want me to go ahead and share?
I think we have to opt that option.
Okay, let me launch it really quick. What do I want to do here? I'll do it with Binder. Give me just a sec. My kernel is finding itself. Oh wait, I don't actually have to do that. Hold on. Let me just launch it from my desktop. I'm being a silly human here. All right, let me go ahead and do a share really quick. All right, can everyone see this? Yoshika, can you see that okay?
Yeah.
Okay. So do you want to present and let me know when I need to scroll?
Yeah, okay.
Okay.
So let's start here. So everyone, I know that mathematics is very daunting, but you don't need to worry. We are not doing everything at one time, and we are taking it in bits, and you can just read the notebook and you will get most of the topics by yourself. We have written it in very easy language. So we chose this path because in NumPy, most of the functions are random functions. So we wanted you to get familiar with what random variables are. So that's why we are starting with maths before NumPy and pandas. So with that being said, what's random variable? So random variable is the heart of machine learning. Like everything revolves around random variables. And in probability and statistics, the random variable is different from the variable that we use in programming. Like if you are familiar with C or Java, the variable that we use there have a fixed value, integer variable or floating variable that has a value that we define. But in statistics and probability, the random variable has no value defined as such, and the value is chosen on the basis of the probability. and random variable are subject to the variations due to mathematical chance. And yeah, so random variable typically represents the possible outcome, like what will be the outcome if this experiment is performed. So it just tells you that what is the end result after you perform this, and that result is totally based on the probability. So there are two types of random variables. Before that, you can represent random variables as either objectively random variables, and that's totally based on the random process, like random thinking or something random you do. And the subjective random process is based on the incomplete knowledge, like you know something, but that's not the complete information you have. So that's also falls under the random category because you don't have the complete information, so you cannot assure that this value will be the answer. So that totally depends on the probability at the end. So there are two types of random variables. One is discrete and the other one is continuous. So discrete random variables uh, represents the outcomes in a single value. Like you have a set of values, and the random variable will uh, give you the outcome based on the probability which is maximum. Like if you have a set of numbers and the number having maximum probability will be outputted. Like here we have a set with 1, 2, 3, 4, 5, and 6. So we roll a dice and we know that we can get 1 or 2 and 3, 4, and 5 or 6. So we will get only one value out of this, which will have the maximum probability. In this case, all of them are equally likely. That means that any number can occur with equal probability. But you know that only one value will be outputted. On the other hand, in continuous random variable, there's a range, and there are infinite values that are possible. Like if I take a range between -1 and 1, you can have any value 0.91, 0.92, or anything. Like there are infinite values possible, and that's also I'm giving you example of -1 to 1. Think of bigger range. There are infinite values possible. So that's continuous random variable, that you have infinite range, infinite set of values in a range. So
Yep.
there are infinite number of possible values, and that are uncountable.
The other way I like to fix this in my mind, and this is just for me personally, is when I think of discrete, I think of points, as you can see here. When I think of continuous, I think of a line, a curve, right? And so on a line, there isn't any one point, there isn't any one thing that you can count. A line is continuous. It has an infinite, right? There's always, 0.000001 more things. So I try to fix that in my mind, although sometimes this can, for me, be a little bit slippery. I draw lots of pictures, as you can see. Go ahead, sorry.
Yeah.
Oh yeah, so there, underneath both of these things, but more underneath the continuous, there are mathematical functions, which if you're anything like me, you had to kind of meditate on your high school years and your algebra and your calculus to remember. But there is an equation that, if you graph it, will form this curve. And that describes that, in this case, probability distribution. And as this diagram shows here, in a continuous distribution, instead of having a fixed point or a fixed outcome, what you have are areas where possible outcomes happen with a certain probability. So 34% chance it's going to be in here, 34% chance it's going to be in there, 13% chance it's going to be in there. And this is where we get the name probability distribution or statistical distribution. So if you had an infinite amount of time to run this experiment infinitely and started to plot all of these points, eventually you'd see the values cluster into this shape that is underneath the curve that is graphed, is the graph of a mathematical function. So it's this whole tower of stuff. And at some point I just kind of say in my mind, okay, random variable equals that whole thing, and I'm going to unfocus my eyes from the details. All right, later on, we're actually going to talk about that scary calculus concept of derivative, which is basically a mathematical equation that describes a line that would intersect this curve at a point. But we're not going to do that today. We're just going to talk about random variables and a few other things. All right, and we have some math refresher links here for you. And I certainly needed to use these as I was going through this material. And if you have doubts, well, drop them in the Slack channel and we'll deal with them. We all have doubts. I have doubts. I'm having doubts right now. All right. Shika, do you want to take equations?
Yeah, I can take the equations.
Okay.
Okay, so what an equation is, it's just a combination of variables. So what is a variable? What is a variable? Again, variable is a value that is not defined at the start, that unlike constants, the variable are not assigned value at the start. Like any number 3, 5, 1 or 8, they are constants, but variable a, b, x, y, you don't know what value is that. So equation is formed. An equation is formed by combining variables and constants all together. Like we'll be combining some variables and constants with some mathematical operation that could be plus, minus, multiplication or division, and the equation is formed. So equations have powers that are called degree. As you can see here, y is equal to 1 by 2 x plus 2. Here y and x both have 1 degree, so this is a linear equation. When degree is equal to 1, the equation is a linear equation. And above you can see y is equal to x squared minus x minus 2. Here the degree of x is greater than 1, that is 2. So this is of second degree quadratic polynomial.
And yes, of course, there's a lot more we could go over in equations. This is just a quick refresher. And for me, I always think of, linear line and polynomial, whatever their degree is a curve with one or more humps in it. I kind of leave it at that and hope that I don't have to, get up in front of anyone and explain it further. Oh, I also wanted to say out loud, Carolina had a great point about continuous variables. Another special thing about continuous variables is that they can be divided infinitely and still have a meaning. Because if you have an infinite number of points, then you have an infinite number of opportunities to divide them. So, which is a great point. All right, so equations, one of the underpinnings. The next underpinning are matrices. Matrices are fun, and matrices really are at the heart of the scientific Python stack. It wasn't until the makers of NumPy went through and defined mathematical precision, because Python does everything in floating point numbers, which does not work for machine learning or for most science. So the makers of NumPy first had to go in and define very specific numeric types that had a fixed space in memory and a fixed definition. And then they went through and defined matrices, which are a special type of array. But matrices allow us to do all sorts of very cool transformations and operations on sets of numbers, and fast. And TensorFlow, if any of you have heard of that, which is a famous Google machine learning library, is essentially this. A tensor is a three-dimensional or n-dimensional matrix. So a matrix that has more than just a height and a width. It has depth to lots and lots of dimensions. And those are very handy for calculations. So a matrix really is a type of array, or if you're thinking in terms of core Python, it's a list of lists. So if you think about this in terms of each row of this being its own list, and then the whole thing being contained in a list, that is a form of matrix. Although the way core Python stores that is inefficient. So when we get to NumPy and we start working with NumPy arrays, you'll realize that NumPy has a different way of storing those that is less flexible than a Python list, but is much better for fast calculation. So matrix has two dimensions. It has a height and a width, or a number of rows and a number of columns. And when you're doing something in NumPy or Pandas, the arrays that are underneath those have to all match in their data type. That's one reason why those libraries are fast. When you're dealing with only one dimension of a matrix, you will hear the term vector. And that's just like a slice of this or a slice of this is mathematically called a vector. You'll hear the word shape, and you'll see the function shape a lot in NumPy, or reshape. Shape is the word we use to describe how many rows or columns are in a matrix. So if something has a shape, and rows go first, has a shape of 4 by 3, it's 4 rows and 3 columns. Or if it's 3 by 3 by 4, it's 3 rows, 3 columns, 4. Oh, typo. I said 3 deep, 4 deep. And then we also have a term rank. So rank helps us keep track of how many, quote, deep something is. So if you have a 4 by 3 by 3, it has a rank of 3. It has 3 dimensions. And you can do various math on these. You can add and subtract and multiply. There are specific rules you have to follow for that. You have to make sure that every element in one matrix is operated on with a corresponding element in another matrix. And addition and subtraction are pretty straightforward. Multiplication is a little bit tricky because of this rule of operating on each element in pairs. So I'll let, I'm gonna be a coward and let Yashika go over the matrix multiplication, if that's okay.
Okay, so to multiply matrices, we need to do a dot product. And a dot product is simply when we multiply the matching numbers from each row of one matrix and corresponding row of another one. Like we have two matrices, or I should say vectors, because this is one dimensional. So 1, 2, 3 is we do the dot product of 1, 2, 3 with 7, 9, and 11. So the first element of this vector is 1, that is multiplied with the second corresponding element, that is 7. Both are at 0th index, so that's why we are multiplying the corresponding elements 1 and 7. Then we are gonna add the elements in the next index, at the next index. So at first index we have 2, and correspondingly we have 9 at the first index, so we are going to multiply 2 into 9, and then lastly we will add 3 and 11. We will multiply 3 and 11 because both of them are at index number 2. So this will give you 58, and yeah, that's it. We match the first members 1 and 7, multiply them, then add the second members 2 and 9, and then multiply them and add to the first members, and then we go on further with 3 and 11.
Yep.
So,
but it gets a little trickier when you're presented with 2 dimensions. So this is where we're doing 2 matrices together. And you want to proceed in a specific order here. So you take the first with the first, and you do this operation above, the dot product. So here you see there we've got 1, 2, and -1, and 3, 0, and -2. So we do 1 times 3, 2 times 0, -1 times -2. And so that becomes this first element here, which is 5. Then you keep the first row, but you do the second column. So that's 1, 2, -1 with 1, -1, 3. So here in this position, whoa, if Bethany can keep her paws off of the notebook, we have a -4. Then in the third step, we go to the second row, first column. You can see there, that's a 4. And then finally, we do the second row and the final column, which is a 5. So the product of this matrix and this matrix is this matrix. But sigh, as with everything, there's rules. You can't multiply 2 matrices together if these dimensions don't match. So if you look below, this doesn't work because when you try to perform that operation where you take this first row to match with this first column, you've got one lonely hanging number here without a partner, which ends up being, quote, undefined. Like I can't, there's no rules for me to like reapply multiplication from one of these. I have to have another number for this number, and there isn't one. And so I can't multiply these 2 matrices together. There's no way to do that. Well, I mean, there is if you perform some other tricks, but in a straightforward fashion, no, you can't do that. Shika, if you want to go over the points to remember.
yeah. So the number of, as she said that the number of columns in the left matrix must be equal to the number of rows in the right matrix. That's like here that if we have 2 cross 3, we can't multiply it with 2 cross 2 because the inner dimensions 3 and 2 are not matching. The inner dimensions, I call it inner dimensions, they should be matching. And in case you have something like 2 cross 3 and here you have 2 cross 3 here as well, then you need to transpose one of the matrix so that the inner dimensions match.
Yeah,
like,
so you can flip them. Yeah, if you transpose this matrix, then the dimensions become 3 by 2, and then you can get away with it. The other thing that I always, oh, go ahead, please.
No, go ahead.
I was going to say the other thing that I screw up on when I'm thinking about matrices is, you know, you spend years being trained that multiplication is transitive, that you could A times B equals B times A. That is not the case in matrix math. That does not work. Even though my brain insists that it does not. All right, and then there's as a hint for the future, there's and I didn't put a picture in, but there's this special kind of matrix called an identity matrix, where you have all ones on the diagonal and zeros everywhere else. That is kind of a magic matrix you use to transform things, which is kind of cool. So, all right, are there any questions so far, or shall we proceed? All good. All right, Karen, thank you. All right, Shika, I'm gonna let you do the probability because probability kicked my butt. Guys, I got a D in my first probability class. My brain is not wired for probability. Chances are really good if I intuitively choose an answer, it will be wrong.
Okay. So probability. So probability is typically hard to explain, but I'm gonna try my best. So probability of any event lies between 0 and 1, and the range is inclusive. We cannot have probability greater than 1 or less than 0, that is negative. Negative probability is not possible. So sum of total probabilities of any event cannot exceed than 1 and cannot be lower than 0. So probability is all about possibility of various outcomes, like we discussed above. In the case of random variables, any event has a certain, like what do we say, like a fixed measure that this is the chance that this will occur. So that chance is probability. Like this is the chance that this will occur, and for different events, we add the probability all together, and then we find the total probability of an event, and that cannot exceed 1. So a random variable, X is a variable, we already discussed this, which takes on randomly chosen values from a sample space. Sample space is nothing but a set of possible values. Like in the case of flipping a coin, you can either get heads or get tails, so that's the sample space. When playing with random variables, each outcome is equally likely to occur. Like if we have unbiased coins, the head and tails both have the probability 1/2 of occurring. Like it's not that head is prioritizing over tail. So every outcome is equally likely to occur. Then moving on to distributions. As a reminder, continuous is something like we can have infinite values, and discrete is we have a fixed value from a set. So values that can be anything between a range are continuous, and values that are specified or complete are discrete. So let's start with the distributions. The first one is Bernoulli distributions. And this is the simplest discrete probability distribution. Like you will not find anything easier than this. In case of Bernoulli distribution, we have only 2 possible outcomes, that is either 0 or 1. And 0 represents the case of failure. Like if we have an outcome that is that depicts the failures or false, then we represent it with 0. And if it's true, success, or yes, it's 1. Like it's similar like we do in Python, 1 and 0 for true and false. So it's similar to that. And here you can see in this image too that for true we have 0.69 probability, and for false, and we can calculate for the false. Like we know that probability cannot exceed 1. So for false and true, these 2 cases, the probability will be the probability of an event to be true plus the probability of an event to be false. So when we have probability of an event to be true, that is 0.69, we can easily calculate the probability for the event to be false. we can do 1 minus 0.69 and then we'll get the probability for that event to be false. And yeah.
Yeah, and so what's interesting about the Bernoulli distribution is that because you've got true and false and it's divided, right, the sample space adds up to 1, then your median and your mode are all 1/2. Because you know, it's 0 or it's 1. And while this just seems very, very simplistic, as you'll see as we go through these distributions, Bernoulli itself might not be interesting, but as you start to add more Bernoulli experiments together, it gets interesting. So, and this over here has your little summary statistics for this distribution. All right, the next one, the uniform distribution. So the uniform distribution is the simplest continuous probability distribution. It doesn't look continuous from this graph, but it is continuous. So Bernoulli models 1 experiment, 1 coin toss, 1 light switch, 1 bit flip. But this distribution represents a range, an infinite range of numbers or outcomes. And they're all equally likely, which is why this is a flat, straight line. And this, you see this a lot for setting a seed for something. If you're doing something in computer science, like a random walk or something like that, you might take values, X number of values from a uniform distribution to seed something. And so here you can see this is continuously 0 until it hits point A, at which point it's continuously a set of values until it hits B, whereas where it drops to 0 again, essentially. So it's also called a rectangular distribution. So the uniform comes from it's uniformly a straight line, rectangular because it looks rectangular on the graph. And so its parameters are, you know, infinity in one direction until you hit A, and then you hit B, and then infinity in the other direction. All right. You want to do binomial, Nishika? So this is where Bernoulli gets interesting, is where we hit binomial.
Should I do this?
Sure.
Yeah, the binomial distribution is a superset of the Bernoulli distribution. Like it's the parent distribution of Bernoulli distribution. In case of Bernoulli distributions, we were having like 0 and 1 Boolean values. In binomial distribution too, we have Boolean values, 0 and 1, Boolean or discrete in the language of probability. But when we have to calculate the possibilities of the same event occurring more than once, like the example I gave you in Bernoulli distribution, like you are flipping a coin. You can either get head or tails, 0 or 1. But if you are flipping the coin multiple times, like you are flipping it 10 times or 15 times, what's the probability of all the events together? So when we want to calculate the possibility of the same event, like we are flipping the same coin again and again, more than one time, then the probability for that event will be represented by the binomial distribution. So here also, like Bernoulli, we have 0 and 1, and every trial is independent of another. Like if you are flipping the coin 4th time, that is independent of flipping the coin 9th time. That two doesn't relate. So a binomial distribution that includes only one trial is a Bernoulli distribution. So the times we flip the coin is known as trial, like 10 trials or 15 trials. As you can see in the graph, we have different values, like these represent the different trials. For the first trial, we have 0.5. For the second trial, we have 0.7. Like these are kind of histogram type of representation that's telling you what's the overall probability of the when we combine all the trials, and all trials combined is known as event.
Yeah, and that's where it's interesting, because if you notice these all, if you were to draw a line through these, they look like different styles of curves, like a sharper or a leaner curve, but this is a discrete distribution. So it's a collection of experiments, and each one of these lines is one of those independent experiments, but then you line them all up and they create this kind of curve shape. And you can go ahead and do this one too if you'd like, Yashika, the normal distribution, which I love talking about because I'm not sure there's anything normal about this, but go ahead.
So a normal distribution is a continuous distribution. Bernoulli and binomial were discrete distributions, but the normal distribution is continuous distribution, and it has values between a specified range, and those values are infinite values. And the curve you can see is bell-shaped. And there's a special thing about this distribution, that the mean, median, and mode, these three terms are statistical terms. Mean is, you can interpret mean as average. So the mean, median, and mode are equal to one another, and also they are placed at the center. If you can see in this graph, the center peak value represents the mean, median, and mode. And for this distribution, there are those three are all equal and here centered at 0. So mu, this is a Greek letter, represents the mean, and it tells you that it's centered at 0. And so when you see right and left, 34.1%, 34.1%, that's standard deviation. As you can interpret from the name, deviation tells you that how much the values are deviating from the mean. Since the mean is centered at 0, the other values, 34.1%, are the values that are deviated from the center mean. And as you go further, 13.6% are the values that are more deviated from the mean. As you go further, the values are more deviated. The values centered to the mean and near to the mean are less deviated, and the values that are far away from the mean are more deviated. So this shaded gray area is this value represents that if a value falls in this region, it has 34.1% chance of being deviated from the mean.
This I find, and if any of you have been in a class that was, quote, graded on a curve, this, which I find a very annoying grading scheme myself, what that really means is that when a teacher goes to give grades, if someone's gotten 100% on a given test or in the class, then this line comes out to 100%, and all the rest of the grades in the class then become distributed based on the mean value from 100, which means that, you know, if you get 70%, you get a C. But if someone does not score 100% on that test and they instead score 80%, then it shifts everything, and 70% is a higher grade. Because they're using this normal distribution to apply to the grades in the class and setting the top grade based on the top score. Which also means that, you know, people who fall into this area are out of luck when it comes to their grades. And I'm always confused by this, about the normal part of this. The normal part of this refers to the fact that this curve is symmetrical around the mean. And so that makes these sections even. And that makes the values evenly distributed on either side of this middle line. And so that, that is where the name normal comes from. That in statistics is a normal distribution of values. Yeah, so. And you can see here the percentages. So something is considered a normal distribution if 68.2% of your possible values in your range fall within one standard deviation of the median line, and so on and so forth. All right, final distribution, Poisson's distribution.
Yeah, go ahead.
Okay, so Poisson's distribution is similar to the binomial distribution in that all the events in this distribution are independent of each other. But there's a difference here. So continuous versus discrete. Binomial distributions are based on discrete events. So that coin flip, that bit flip. Poisson is based on continuous events. So binomial distribution is based on events that have a fixed number of attempts. I pull the arm of the gambling bandit, 10,000 times. I flip the coin 500,000 times. But the Poisson distribution is based on events that have an infinite number of attempts, but in a very specific time period. So this is used to model events that could happen possibly an infinite number of times, but they don't happen that often. So they happen with a cycle or a pause in between. So a very common example is, or they're spaced in intervals such as distance or area or volume. So meteor showers. Meteor showers may occur once a decade, but when they do, there's a lot of them at once. Bus arrivals. Buses may arrive every 15 minutes, or subscription renewals. So anything that happens or repeats in a cycle and can be plotted in a time series is usually the way I think about this distribution. So here the delta is the interval for this. And so here you can see an interval of 1, an interval of 4, an interval of 10, and the events that are happening over time for this. Earthquakes, yes. Catalina, that earthquakes are a great one. They may not happen that often, although if any of you have looked at the USGS site, don't do that if you're afraid of earthquakes, because there are a lot more than you would realize. As it turns out, where I live in California, the earth is almost constantly moving. It just happens to be moving below our threshold of perception. But yes, earthquakes, yeah, but when they happen, boy, they happen. That is it exactly. So that is the Poisson distribution, and it is super, super useful for those cyclic events or those spaced events. And that is it for our overview. We, as we said, kind of did a quick overview of the math, and we have some time. So I don't know if we want to kind of have a discussion or talk about these things, or if any of you who are statisticians or who are practicing machine learning or data science want to chime in with your experiences with this stuff. That would be awesome. Someone is in a neighborhood where a dog is angry. I'm hearing a barking dog there. This recording will be available. It's not going to be available directly after the webinar. We have some very hardworking volunteers. In fact, I think one of them is attending tonight, Sarah, who go through these recordings to make sure that they're clean and that we didn't pick up anything we weren't supposed to in a screen share or so forth. So it takes us a little bit, but we do make the recording available. Yes. I'm going to stop my screen share here, and please feel free to chime in with questions or just with comments. Did we go too easy or too hard on you? Are we going too fast? Are there these scary Greek characters that you want us to explain to you? I myself have had to make a magic decoder ring for all the Greek. In fact, Yashika and I both were saying that, you know, we never intended Greek to be a second or even a third or fourth language. Nevertheless, here we are learning Greek. Mathematical Greek, at least, not actual Greek. What would be an example of the uniform distribution? That's a great question, Catalina. Does anyone have, off the top of their head, a phenomenon or a thought about what would be represented by a uniform distribution? Like what real world event would be represented by a uniform distribution? I don't. I could Google, but if someone has one. Nishika, you want to save me? I can Google it.
I think the rolling the dice would also fall for this uniform distribution. Rolling a dice would be an example.
Oh yeah, as a single roll. Yeah. Yeah, that makes sense. But I wonder if there's another one. I'm looking, well, let me see what Wikipedia has to say. Yeah, and we didn't, I forgot to go over, this can either be a closed or an open. So the difference, yeah. Intervals are the same like the, or it's equally probable. Yeah, you know, Wikipedia does not actually give an example except for the dice. See if Wolfram has anything. Nope, Wolfram just has a lot of math.
There is this example. I'm not sure if this is right, but I'm gonna say it. It says the last digit of the social security number, the goalkeeper for the US World Cup team is about equally likely to be any digit from 0 to 9.
Oh, that's interesting. That's a really interesting one.
What do you think?
Well, yeah, so the way they assign social security numbers is that the first, oh, now I'm gonna have to look it up again, but I think the first three numbers is your time period, then the next three are your region, and then the final three identify you. No, I take that back. The first three are the region. The next three are the location, and then the final three are the first two are the birth date, and then the final one is assigned in order for all births in a given like time, so like in a given month. So yeah, that would make sense because that final number goes, you know, the first one goes, the first baby born is 0, then 1 through 9, and then it starts over. So yeah, then it would be equally likely because it cycles through.
Yes. Yeah. Okay, what about this other one? I thought that was interesting too. The date of the week of the hottest date of the year is about equally likely to be any of the 7 days. I don't know about that, but I'm not sure.
Yeah, I don't know. We would have to look at the data for that.
Yeah.
That's interesting though.
Yes, it could be something to investigate, I think, but I think it could be. It could be.
Yeah. I mean, I guess that's the thing. If you take a look at your data, right, at the distribution of your data, and you see it starting to form up into that shape, right, then, you know, you've got equally likely outcomes. And so if all the outcomes are equally likely, then it's uniform.
Yeah.
Yeah, uniform or universal, because they're lined up. But you have to make sure they really are equally likely for the duration of the experiment. Yeah. So Gloria says, going back to the matrix equations, you mentioned that a matrix doesn't have an equal number of corresponding values, cannot be solved by multiplication. Could you share an alternative way of solving that kind of equation? Well, Yashika mentioned that. So it is possible. You have to, the short answer is, if you can, by some trick, make those dimensions match, that's your get out of jail free card. Now, that doesn't always happen, but there are some tricks you can employ. One of them is to transform one of the matrices. Transform meaning take, so if we go up here, this matrix here, if you were to transform.
You're not sharing anything right now.
Oh, thank you, Liliana. I have to share my screen. Yeah, like I'm just talking to myself and no one can, can see what I'm talking about. All right, I'm sharing now. Okay, so this matrix here, if you were to do a transform or a transpose on this matrix so that the rows became columns and the columns became rows, then you've changed the dimensionality of this, and then they can be multiplied. Another trick you can employ is this identity matrix. Sometimes what you can do is do a multiplication with an identity matrix that will then transform the matrix to make the dimensions match.
And one thing, yeah, you
ahead.
can do, yeah, when you have two matrices that those dimensions doesn't match, like if you have a matrix that has 3 columns and another matrix has 2 columns and you want to make it with the same dimension, so you can add one column with values full of zeros or ones. When we will go with NumPy, we will see that there are ways to create matrices with the values full with zeros and ones. So you can increase the dimensions by adding a column of zeros and ones.
Yeah, so you can pad the dimensionality of one of the matrices with zeros, right? And zeros are going to zero out the values. So we can dig into that a little bit more, right? There are penalties and considerations for each of those methods, for doing a transform or for doing an identity multiplication or for doing padding out. But yes, those. So as the short answer is, you have to make a match by hook or by crook. And some of those transformations are more elaborate than others in making them match. And sometimes you cannot make the match, which means you have to solve the equation through other means. Yeah. All right, Liliana is nagging me that we're getting close to closing time here because it's 7:21 my time. So does anyone have any other questions or any requests for material that we either add to supplement this, or things we might be wanting to go over next time? Now would be the time to add it. And if no one has any requests now, you can always pop into the Slack channel and let us know. Also, the next session, which will be 2 weeks from now, we will be, Yashik and I will be going over more of this math and more of how to solve this math using the computer, because we're programmers and doing this in your head is just crazy. Or at least I find it crazy. Maybe you don't find it crazy, but I find it crazy. I prefer to have the machine do it because the machine doesn't make the mistakes I do. And so we'll be taking a little bit of a look at NumPy and at doing some linear algebra with the computer assist. And also feel free, I mean, if you guys find, you all find out there a problem, whether it falls into the probability category, for which I will probably defer to Yashika because, like I said, probability is my Achilles heel, or linear algebra with the matrix transformations, or about distributions or random variables, you can go ahead and drop that in the Slack channel and we can discuss it next week, or not next week, but next session, or right in the Slack channel. It takes a while to dig into all of this stuff, and I think we're gonna just, my strategy personally is to loop around on it until I kind of beat it into my brain. All right, well, thank you so much. Let me just put up the thank you so much slides. Oh, and we'd also like to remind you, actually I need to stop my screen share here and reshare my screen. So I'll go ahead and do that. There we go. We'd also like to encourage you to get involved if you haven't already. I know many of you have. We would love to help you. We'd love to have your help in growing Women Who Code Python. We're always looking for leads and for evangelists, so you can go ahead and sign up at womenwhocode.com/Python. And you can also join the conversation on Twitter, on Instagram, on Slack, that little scan code. We're at wwCode Python. So thank you again for attending and for your patience.